And the next one is a similar one given by Karel Veselý on boosting of the contextual information in ASR for air traffic call sign recognition. So Karel will tell us more about the technical part inside.
Yeah, hello. Yeah, so obviously we work on the same project and we share some resources. So from my point of view, it will be more focused on how this contextual adaptation works under the hood. And we did some extra experiments on that. So what we have, so first of all, to give some framework, what we do contextual adaptation for ASR. We do it by means of WFST composition. And for us, the context really changes quite rapidly. So in our case, we change the context from sentence to sentence. And we like focus on basically to get the call signs appear correctly in the ASR output. That's our goal in this talk. Well, as many of you know, call sign is a sort of like verbal identification of the plane that's said by the operators or by the pilots. And there are three examples. How does it? Okay, can I use the pointer? Does it work to show the? Ah, yeah, it's okay. Yeah, okay. This one. Yeah. Okay. Yeah, so we have three examples of call signs. So there is both the like verbalized form or the like the concentrated form, which is used in the radar system. And so basically there is some airline designator that's typically one or more words plus some sequence of digits and letters. Okay, go to next slide. So what we do, the airplane is sending some messages which are captured by either the radar system or the enthusiasts stored in the database. So we have some like some time, space information. Like basically, we can ask queries of the type. We have some location, some time frame, and give me the list of the call signs which appeared in this area. And so we can use this information to help ASR have the call sign correctly on its output. And our goal is, well, basically that's what I just said. Here I would like to say a few words about the challenging aspects of the call sign recognition, why it's a problem. Well, in one of the previous presentations, there was like they had accuracy of 96% for the call signs, but when the data are more noisy, it's becoming more difficult to recognize them correctly. And also there is a lot of airline designators. There are like more than 7,000 of them in total that we have in the table in our system. There are also some unofficial variants that the longer ones, they get abbreviated just to gain some speed, like Lufthansa gets shortened to Hansa, Speedbird to Bird. There are also some shortenings. Oh, sorry. Shortenings of the call signs are allowed in the standard. That typically for the first initial contact is the full call sign, but then like the last two positions or a little bit more is allowed. Just to, if it's not ambiguous, it's okay. And also there are these different variants for the verbalization. That, for instance, there should be 3 zeros in this place. So either it's possible to pronounce as 000 or 000 or 000. So this like gives more variability. The possible applications, so it could be good for basically to track in the communication where the call sign happens. So this could be for the, let's say, real-time applications, or for the offline post-analysis of the recordings if there is some incident, and so that the investigators, they could look up in the database, query for that call sign, and this could help them work faster. Or it's possible for like communication error detection. If like wrong call sign is set on the air, this could be used to detect this. And also for cockpit use, that sometimes the pilots, there are these problems with the local accents, so that could help them if it's shown on some system, or it's good, like, assist them. So how we do this under the hood? we use lattice boosting, and also after lattice boosting, or actually before in the ASR processing, we could also do it in the recognition network. We can do the boosting. So for now, the lattice boosting, the way the ASR systems work, that they produce the lattice, and then in the lattice we can modify the scores to, let's say, suggest like what outputs are expected from the ASR system, which improves the results. So first, for this, we get this list of call signs. We first verbalize them. Typically, there are several variants because of the possible variability, so we try to include all of them. The boosting, the way it works, we boost each such word sequences as the whole snippet of text. So if it's just occurring only partially, it gets no score discount, only if it's there as the whole thing. The way we do it by WFST composition. So we have lattice L, we compose it with some boosting graph B, and we get like updated lattice with changes in the scores. And in this boosting graph, each such word sequence that is boosted is represented as like a specific path in that graph, and the words on that path have some score discounts. So these discounts, in the lattice we have language model scores, which are included as graph scores in case of Kali, and we give some offset to these language model scores, which is why this is how we make them like appear on the one best output of the ASR system more likely. So, and we change this boosting graph B from utterance to utterance, and finally the modified lattice we just decode it to get the one best output, and that's basically it. It's pretty much similar way that Google does it in our cell phone ASR recognition. That here I'm showing how the boosting graph looks like. So in our case we have the upper part and lower part. Upper part is this section, so this is where these score discounts are. So we can see that there is a path like CSA 3 alpha bravo, or if it's shortened, it's just CSA alpha bravo without this word 3. The scores here, this -6 and 4, those are the score discounts, just examples. And by epsilon link, we return to the initial state, which is also the final state. And so here are the call signs. There can be like lots of call signs. All those which are boosted would appear here. And then we need some background model to cover the words which are not included in the call signs, so that we don't like discard such words from the lattice, because we are using the phi composition. We are using the composition, and in order to preserve them, we need to do it this way. Yeah. Okay, there is one implementation detail. So we use phi composition, so that the idea is that we visit the lower part only if it cannot be meshed with the upper part. So this is done with this phi symbol, this hash 0. Well, we could also do similar thing by the sigma matcher of OpenFST, but we did not implement this. But then we could like even not have this lower part at all, and the boosting graph would be smaller. But that's for future. We need to like re-implement it. But yeah, the results should be the same for both implementations. It would be just a little bit simpler. And the like limitation of this boosting method is that the word sequence that we want to boost, it really has to be present in the lattice in order to be boosted. So if it's not there, what we can do is to apply this HCLG boosting. That conceptually similarly, we have the recognition network. It's just different graph from WFST. It doesn't care if it's lattice or recognition network or some other graph. If just the semi-rings are compatible, we can apply composition and put some boosting discounts by composition. in this case, yeah, this is to like make some rare words more likely to appear in the lattice. That especially for these airline designators, there is lots of them, and some are similar. And it could happen that if it was not appearing by like giving some score discount, we can like help it appear in the lattice to further like help the boosting to work better. Yeah. And yeah, there is the problem is the runtime here. That this HCLG graph, it tends to be quite large, so we cannot just use the same topology as we used before. So we use this like simplified form. So we are boosting like isolated words here. So. And we chose to apply it on the rare words only. So this could be also like single state graph with the self loop, just for the sake of presentation. I visualize it here as like two state graph with the backlink through epsilon to the state 0. And so here are some experiments. So we try to simulate the case that we deploy ASR to a new airport, because it's this very practical way to think about it this way. And we are evaluating both the word arrays and the call sign accuracies. That in this study we used some system for the call sign recognition, which is it's a neural network which gets the word sequence from the ASR and identifies this compressed format of the call sign. This is, yeah, I think there might be some ASRU paper describing how they do it exactly. And here you can see that for the word array there is this leaf ATC test set 2. It's a bit noisy. That's what we collected and transcribed in the project. So initial word rate was 33.1, and just by boosting call sign, the overall word rate of the whole set improves quite a lot to 28.9 by lattice boosting. Or if we do the HCLG plus lattice boosting, we get some like 0.5% better result than before. But more interestingly, in this call sign recognition, the scores improve quite a lot. That before we had like 53% accuracy, and just by lattice boosting it improves to 75. And if we include also the HCLG, it further jumps to 80%, which is approaching our Oracle call sign accuracy that we have. Plus there are some characteristics on the test sets that this is more noisy. Mallorca Vienna is more clean, and it's the operators only. And from Hawaii we have this Iceland, the Keflavik airport and London airport here, and for all of them we consistently see that there are the word rate improvements happening. Yeah, so to conclude, yeah, it works. This combination of HCLG and lattice boosting helps to correct the call signs in the best ASR hypothesis. We got word rate and call sign recognition accuracy improvements, and this is a generic method. So whenever we have some application scenario where we have like snippets of text that are likely to appear, which changes quite rapidly, we could use this framework. And if we identify like list of rare words for this HCLG boosting, it's possible to use it. So just to repeat that the context, it changes from utterance to utterance, so it's quite flexible. So these are the two projects that we work on currently, and I would like to thank you for your attention.
Thank you very much, Karel. So we have some time for questions also. Anything from the audience? Yep.
I actually didn't understand the point in this lattice boosting. Why do you have this background word there? Like this lower part?
Okay.
Is it something which needs to be there, and how do you actually compose that? Is it?
Yeah, there is the thing is that in the OpenFST, for the composition, there are like 4 different matchers, we are using the phi and if you use the default matcher, if you need to, let's say, you have some lattice and you have to support in the boosting graph an arbitrary word sequence, so that you keep the original lattice, all the paths remain there. If you would like not have this, it would just keep the call signs, and all the rest would be discarded.
But how do you actually compose it? It's because it's kind of like background model, right? Like
it's kind of background model just to match, like to support arbitrary word sequences. But that's one thing. It could like double the number of paths because of this, pretty much, by the composition. If we use the phi composition, it just matches the call signs, and if it cannot match, then it goes through this phi symbol to the this whole list of words in the lexicon.
Ah, so you use the full lexicon for
that? Yeah, in there. Yeah. And in case that the way that Google does it, they use special matcher, which is for the sigma composition, and there the boosting graph would have a sigma arc, which can be matched to any word. So instead of this background model, there is single arc which matches to everything. But this is not yet implemented in Kaldi, so after it gets implemented and tested, we could like switch to start using the other way.
Okay, thank you very much, Karel. Yeah, one more question. Okay.
Yeah, thank you. I think you mentioned, but I want to ask again, why in this HCLG boosting you boosted just separate, individual words, but not sequences?
Yeah,
it's possible, yeah.
Well, I tried the sequences, but then one composition can take like 5 minutes or more. So then it's not possible to use it in the real-time scenario.
Okay, but this works in real time.
This one, this HCLG boosting, it adds like 25% to the runtime, so that's sort of affordable to do it that way.
Okay, yeah, thank you.
Okay, so let's thank Karel once again and his presentation.